So I'm going to do my best to keep the rotation review under 5 minutes, but this was by far our most complex unit, whether this is you're an AP Physics 1 student or an AP Physics C mechanics student. There were basically 4 things that we talked about: rotational kinematics, torque, which is the force equivalent for rotation, rotational energy, and rotational momentum, which we more often is called angular momentum. So the rotational kinetics was, for the most part, pretty straightforward. Your XYZ becomes a theta, V becomes an omega, A becomes an alpha. But if you look at the 3 equations at the top right, those are the same 3 kinematic equations that you used back in the very beginning of the course in both linear motion and projectile motion. Our units are almost the same. The word meters is replaced with the word radians. So theta is in radians, omega is radians per second, alpha is radians per second squared. And then you see the 3 equations at the bottom center. That is how you translate between linear and rotational information. This moment of inertia chart is a big deal. I will be putting this chart as a link reference into the Google document that we're using for CLP 2.0. And so ideally, as you're watching this video, it would be there, and it's a good reference for you. I strongly recommend you have this file open and ready if you're taking the AP exam. I know it's open book, and this is a part of the book, if you will, book in quotes, that you want to have available for you. And a reminder of what moment of inertia is: it's how mass is distributed about the axes of rotation. The farther away the mass is from the axis of rotation, the larger the moment of inertia. Torque is the force equivalent, is the rotational equivalent of force. There are 2 equations we use. The first one is the sum of torques equals I alpha, or as you see here, alpha equals the summation of torques over I. The second one is how to calculate torque directly for a given force. It's the lever arm times force times sine theta. Theta would be the angle between R and F. Now, if you remember on the energy review, I made it a point to say that energy can be in Newton meters, but advise using just joules for that. That's because torque, the units are Newton meters, and unless we know a delta theta that the torque has swept through, we don't know how much rotational energy was applied. We do know the torque, that's Fr, but we need the delta theta as well, and that's a different delta theta than you're looking at the sine theta here. The next component was rotational energy. Rotational energy looked very similar to translational energy. Instead of a 1/2 mv squared, it's a 1/2 I omega squared. Just like kinetic energy, this must be greater than or equal to 0 at all times. Now there's a point that we call rolling without slipping. In rolling without slipping, that guarantees V equals R omega. In order to roll without slipping, you have to have enough friction where your rolling object is in contact with the ground. If there's not enough friction there, and that friction is static, not kinetic, if there's not enough friction there, it will begin to slide, like a block sliding down the ramp. A good example would be your tires in the snow. As they spin and spin and spin and spin and spin, and you're not going anywhere, that would be a perfect example where V does not equal R omega. However, when your tires get back onto the concrete road, V equals R omega. The last bit was rotational momentum, or as is more commonly referred to as angular momentum, L equals I omega. Now, similar to linear momentum, this has to be conserved unless there's an external torque. Now, this is where it gets interesting, because just like in momentum, you can have collisions and explosions in which the momentum is conserved, but the kinetic energy is not. The same thing can happen in rotation. The angular momentum is conserved, but the rotational kinetic energy is not. And the best way to view that, think about that, is the figure skater, as he or she has their arms extended outwards. that is causing mass to be distributed very far away from the axis of rotation, which means you have a very high I value. Now, as the skater pulls their arms inwards, that mass is no longer far, far away from the axis of rotation. It's getting closer and closer and closer. That's going to cause the I value to decrease. As the I value decreases, since the skater pulled his or her own arms in, that was an internal force creating an internal torque. Therefore, the angular momentum must be conserved, and as the I value decreases, the omega value increases. Now, if you think about rotational kinetic energy, 1/2 I omega squared, if I goes down and omega goes up, well, we know that an angular momentum would be conserved, which means for sure in rotational energy it is not. That's because the skater actually has to exert a lot of force to pull their arms inwards. Naturally, their arms want to stay outwards. And our next one will be electrostatics if you're AP Physics C. If you're AP Physics 1, it'll be simple harmonic motion. Whoops. Goodbye.